हे गाइस, तो आज हम रीडिंग करने वाले हैं चैप्टर 2। ठीक है, फिजिक्स का चैप्टर 2 है यूनिट्स एंड मेजरमेंट। रीडिंग करने वाले हैं फुल एनसीईआरटी। ठीक है, तो चलो स्टडी करते हैं। चैप्टर 2 यूनिट्स एंड मेजरमेंट, इंट्रोडक्शन। ठीक है, तो इधर अपना वो लिखा है, टॉपिक है इंट्रोडक्शन। इसमें है द इंटरनेशनल सिस्टम ऑफ यूनिट्स है, फिर जाकर मेजरमेंट ऑफ लेंथ है, फिर इसी में है मेजरमेंट ऑफ मास है, फिर इसी में है मेजरमेंट ऑफ टाइम, फिर इसके बाद है एक्यूरेसी प्रिसीजन ऑफ इंस्ट्रूमेंट एंड एरर इन मेजरमेंट है, फिर इसी में है सिग्निफिकेंट फिगर है, इन डायमेंशन ऑफ फिजिकल क्वांटिटीज है, एंड फिर उसके बाद है डायमेंशनल फार्मूला एंड डायमेंशनल इक्वेशन है, फिर डायमेंशनल एनालिसिस एंड इट्स एप्लीकेशन है, फिर उसके बाद समरी है, एक्सरसाइज है, फिर उसके बाद एडिशनल एक्सरसाइज है। ठीक है, तो हम लोग यहाँ पहला चैप्टर है यूनिट्स एंड मेजरमेंट, इसका इंट्रोडक्शन है। measurement of any physical quantities involving a comparison with a certain basic arbitrarily chosen internationally accepted reference standard called unit. The result of a measurement of a physical quantity is expressed by a number or numerical measure accompanied by a unit. Although the number of the physical quantities appear to be very large, we need only a limited number of units for expressing all physical quantity, since they are interrelated with one another. The unit for the fundamental or base quantities are called fundamental or base unit. The unit of all physical quantity can be expressed as a combination of the basic unit. Such a unit obtained for the derived quantities are called derived unit. A complete set of these units, both the base units and derived units, is known as the system of unit. The international system of units. In earlier times, scientists of different countries were using a different system of units for measurement. Three such systems, the CGS and FPS or British system and the MKS system, were in use extensively till recently. The base unit for length, mass and time in these systems were as follows. In CGS system, they were centimeter, grams and second respectively. In FPS system, they were foot, pound and second respectively. In MKS system, they were meter, kilogram and second respectively. The system of unit which is at present internationally accepted for measurement is the system international de units, French for international system of unit, arbitrated as SI. The SI, with the standard scheme of symbols, unit and abbreviations, was developed and recommended by General Conference on Weights and Measures in 1971 for international uses in scientific, technical, in industrial and commercial works. Because SI unit used decimal system, conservation within the system are quite simple and convenient. We shall follow the SI units in this book. In SI, there are 7 base units as given in table 2.1. Besides the several base units, there are two more units that are defined for a plane angle del theta as the ratio of length of arc del s to the radius r, and b solid angle del del ohm as the ratio of the intercepted area del A of the spherical surface. Describe about the apex G to apex O as the to the square of its radius r as shown in figure 2.1a and b respectively. The unit for plane angle is radian with the symbol rad, and the unit for the solid angle is straight radian with the symbol SR. Both these are the dimensionless quantities. Del theta is equal to del theta is equal to del s upon r radian. del del ohm is equal to del a upon area square steradian. Description of a plane angle del theta and b solid angle. SI base quantities and units. Table 2.1. Base quantity, name, symbol, definition. SI unit. SI unit. Length, meter, small m. The meter is the length of the path traveled by light in vacuum during a time interval of 1 by 299.792 of a second, 1983. Mass, kilogram, kg. The kilogram is equal to the mass of the international prototype of the kilogram, a platinum iridium alloy cylinder kept at International Bureau of Weight and Measures at Serve near Paris, France, 1889. Time, second, small s, small s. The second is the duration of 99192631770 period of the radiation corresponding to the tradition between the two hyperfine level of the ground state of the cesium 133 atom 1967. Electric current ampere, capital A symbol. The ampere is that constant current which if maintained in two straight parallel conductors of infinite length of visible circular cross section and place 1 meter apart in vacuum would produce between these conductors a force equal to 2 into 10 the power minus 7 Newton per meter of length 1948. Thermodynamic temperature Kelvin. Thermodynamic temperature Kelvin. Symbol capital K. The Kelvin is the fraction 1 by 273.16 of the thermodynamic temperature of the triple point of water 1967. Amount of substance mole symbol mole small mol. The mole is the amount of substance of a system which contains as many elementary entities as there are atoms in 0.0012 kilogram of carbon 12 1971. Luminous intensity candela CD. The candela is the luminous intensity in a given direction of a source that emit monochromatic radiation of frequency 540 into 10 the power 12 hertz and that has a radiant intensity in that direction of 1 by 683 watt per steradian in 1979. The value mentioned here need not be remembered or asked in a test. They are given here only to indicate the extended of accuracy to which they are measured with progress in technology and measuring technique get improved, leading to measurement with greater precision. The definition of base unit are revised to keep up with this progress. Some units are retained for general usage through outside SI name symbol value in SI unit minute mean 16 second hour small h 16 minute is equal to 3600 second day small d is equal to 24 hours is equal to 86,400 second year small y 365.25 days equal to 3.156 into 10 the power 7 second degree degree 1 degree is equal to pi upon 180 radian liter capital L 1 dmq is equal to 10 the power minus 3 small mq. Turn small t 10 the power 3 kg. Carrot small c 200 mg. Bar 0.1 mpa is equal to 10 the power 5 pa. Curie ci 3.7 into 10 the power 10 10 yes minus 1. Wrote Jane capital R 2.58 into 10 the power minus 4 C upon kg. Wrote Jane quintal small q and 100 kg. Burn small b 100 fm square is equal to 10 the power minus 28 m square. R small a 1 dam square is equal to 10 square m square. Hectare small h a 1 hm square is equal to 10 the power 4 m r m square 10 the power 4 m square. Standard atmospheric pressure ATM 1 2 3 4 5 1,01,325 pa is equal to 1.013 into 10 the power 5 pa. Note that when mole is used, the elementary entities must be specified. These entities may be atoms, molecules, ions, electrons, other particles, or specified groups of such particles. We employ unit for some physical quantities that can be derived from the 7 base unit. Appendix A6 some derived unit in term of the SI base unit are given in Appendix A 6.1. Some SI derived unit are given special name Appendix A 6.2, and some derived unit make use of this unit with special name and the 7 base unit Appendix A 6.3. These are given in Appendix A 6.2 and A 6.3 for your ready reference. Other unit retained for general usage are given in table 2.2. Common SI prefix and symbol for multiple and submultiples are given in Appendix A2. General guideline for using symbol for physical quantities, chemical element, and nucleid are given in Appendix A7, and those for SI unit and some other unit are given in Appendix A8 for your guidance and ready reference. Measurement of length. You are ready familiar some direct method for the measurement of length. For example, a meter scale is used for length from 10 to the power minus 3 meters to 10 to the power 10 to the power 2 meter. A vernier capillary is used for length to an accuracy of 10 to the power minus 4 meter. A screw grug and a spirometer can be used to measure length as less as to 10 to the power minus 5 meter. To measure length beyond these range, we make use of some special indirect method. Measurement of charge distance. Large distance such as the distance of a planet or star from the earth cannot be measured directly with a meter scale. An important method in such cases is the parallaxes method. When you hold a pencil in front of you against some specific point on the background, a well at a look at the pencil first through your left eye, your left eye closing the right eye, and then look at the pencil through your right eye be closing the left eye. You would notice that the position of the pencil seem to change with respect to the point on the wall. This is called parallax. The distance between the two point of observation is called the basis. In this example, the basis is the distance between the eyes. To measure the distance capital D of a far away planet capital S by the parallax method, we observed it from two different position observatories A and B on the earth, separated by distance AB is equal to small b at the same time shown in figure 2.2. We measure the angle between the two directions along which the planet is viewed at these 2 points. The triangle ABS in figure 2.2 represented by symbol theta is called the parallax angle or parallelistic angle. As the planet is very far away, small b upon capital D less than 1, and therefore theta is very small, then we approximately take AB as an arc of length small b of the circle and the center at capital S, and the distance capital D as the radius AS is equal to BS, so that AB is equal to small b is equal to d theta, where theta is in radians. Capital D is equal to small b upon theta. Figure 2.2 parallax method. Having determined D, we can employ a similar method to determine the size or angular diameter of a planet. If small d is the diameter of the planet and alpha the angular size of a planet, the angle subtended by d at the earth, we have alpha is equal to small d upon capital D. The angle alpha can be measured from the same location on the earth. It is the angle between the two directions when two diametrically opposite point of the planet and viewed through the telescope. Since capital D is known, the diameter small d of the planet can be determined used using equation 2.2.
Example 2.1. Calculate the angle of A 1 degree, B 1 arc minute of arc or arc mean, and C second of arc or arc second in radians. Use 360 degree is equal to 2 pi radian and 1 degree is equal to 16 arc minute and 1 arc is equal to 16 second of arc. Answer A. We have 360 degree is equal to 2 pi radian, 1 degree is equal to pi upon 180 radian is equal to 1.745 into 10 the power minus 2 radian. B. 1 degree is equal to 16 arc minute is equal to 1.745 into 10 the power minus 2 radian, and 1 arc is equal to 2.908 into 10 the power minus 4 radian, 2.91 into 10 the power minus 4 radian, and C 1 arc is equal to 16 second arc is equal to 2.908 into 10 the power minus 4 radian. 1 second arc is equal to 4.847 into 10 the power minus 4 radian, or 4.85 into 10 the power minus 6 radian. Example 2.2. A man wishes to estimate the distance of a nearby tower from him. He stands at the point A in front of tower C and stop a very distant object O in line with AC. He then walk perpendicular to AC up to B, a distance of 100 meter, and looks at O and C again. Since O is very distant, the direction BO is particularly the same as AO, but he finds the line of sight of C shifted from the original line of sight by an angle theta is equal to 40 degree. Theta is known as parallax. Estimate the distance of tower C from his original position. A. Figure 2.3. We have parallax angle theta is equal to 40 degree. From figure 2.3, AB is equal to AC tan theta. AC is equal to AB upon tan theta. 100 meter upon tan 40 degree is equal to 100 meter upon 0.8391 is equal to 119 meter. Example 2.3. The moon is observed from two diametrically opposite points A and B on Earth. The angle theta subtended at the moon by the two directions of observation is 1 degree 54 arc. Give the diameter of Earth to be about 1.276 into 10 the power 7 meter. Compute the distance of moon from the Earth. Answer. We have theta is equal to 1 degree 54 arc is equal to 114 is equal to 114 into 16 arc bracket close into next bracket 4.85 into 10 the power minus 6 radian is equal to 3.332 into 10 the power minus 2 radian. Since 1 second arc is equal to 4.85 into 10 the power minus 6 radian, also b is equal to small b is equal to capital AB is equal to 1.276 into 10 the power 7 meter. Hence from equation 2.1 we have the earth moon distance capital D is equal to small b upon theta is equal to 1.276 into 10 the power 7 upon 3.32 into 10 the power minus 2 is equal to 3.84 into 10 the power 8 meter. Example 2.4. The sun's angular diameter is measured to be 920 second arc. The distance capital D of the sun from the earth is 1.496 into 10 the power 11 meter. What is the diameter of the sun? Answer. Sun's angular diameter alpha is equal to 920 second arc is equal to 920 into 4.85 into 10 the power minus 6 radian is equal to 9.31 into 10 the power minus 3 radian. Sun diameter small d is equal to alpha capital D alpha into capital D is equal to 9.31 into 10 the power minus 3 into 1.496 into 10 the power 11 meter is equal to 1.39 into 10 the power 9 meter. Estimation of very small distance size of a molecule. To measure a very small size like that of a molecule 10 the power minus 8 meter to 10 the power minus 10 meter, we have to adopt a special method. We cannot use a screw gauge or similar instrument. Even a microscope has certain limitations, and optical microscopes use visible to look at the system under investigation. As light has wave-like feature, the revolution to which an optical microscope can be used is the wavelength of light. A detailed explanation can be found in class 12 physics textbook. For visible light, the range of wavelength is from about 4,000 angstrom to 7,000 angstrom. One angstrom is equal to 10 the power minus 10 meter. Hence, an optical microscope cannot resolve the particle with size smaller than this. Instead of visible light, we can use an electron beam. Electron beam can be focused by properly designed electric and magnetic field. The revolutions of such an electron microscope is limited finally by the fact that electrons can be also behave as a wave. You will learn more about this in the class 12. The wavelength of an electron can be as small as a fraction of an angstrom. Such electron microscope with a revolution of zero point 0.6 angstrom have been built. They can almost resolve atom and molecules in a material. In recent time, tunneling microscopy has been developed in which again the limit of revolution is better than an angstrom. it is possible to estimate the size of molecule. A simple method for estimating the molecular size of oleic acid is given below. Oleic acid is a soapy liquid with large molecular size of the order of 10 the power minus 9 meter. The idea is to first from monomolecular layer of oleic acid on water surface, we dissolve 1 centimeter cube of oleic acid in alcohol to make a solution of 20 centimeter cube. Then we take 1 centimeter cube of this solution and dilute it to 20 centimeter cube using alcohol, so the concentration of the solution is equal to 1 by 20 into 20 centimeter cube of oleic acid upon centimeter cube of solution. Next, we lighting sprinkle some lycopodium powder on the surface of water in a large throw we put one drop of this solution in the water. The oleic acid drop spreads into a thin, large and roughly circular film of molecular thickness on water surface. Then mm, quickly measure the diameter of the thin film to get its area. Suppose that we have drop small and drop in the water. Initially, we determine the approximate value of each drop. We centimeter cube volume of small n drop of solution is equal to small n capital V centimeter cube. Amount of oleic acid in this solution is equal to small n capital V upon capital V in bracket 1 by 20 into 20 bracket closes centimeter cube. This solution of oleic acid spread very fast on the surface of the water and form a very thin layer of thickness small t. If this spread to form a film of area a centimeter cube, then the thickness of the film small t is equal to volume of the film upon area of the film small t is equal to small n small nv upon 20 into 20 a centimeter. If we assume that the film has monomolecular thickness, then this become the size of diameter of a molecule of oleic acid. The value of this thickness comes out to be of the order of 10 the power minus 9 meter. Example 2.5. If the size of a nucleus in the range of 10 the power minus 15 to 10 the power minus 14 meter is scaled up to the tip of a sharp pin, what roughly is the size of an atom? Assume tip of the pin to be the range 10 the power minus 5 meters to 10 the power minus 4 meter. Answer: the size of a nucleus is in the range of 10 the power minus 15 meter and 10 the power minus 14 meter. The tip of a sharp pin is taken to be in the range of 10 the power 5 meter and 10 the power minus 4 meter. Thus we are scaling up by a factor of 10 the power 10. An atom roughly of size 10 the power minus 10 meter will be scaled up to a size of 1 meter. Thus, a nucleus in an atom is as small in size as the tip of a sharp pin placed at the center of a sphere of radius about a meter long. Range of length. The size of the object we come to across in the universe vary over a very wide range. These may vary from the size of the order of 10 the power minus 14 meter of the teeny nucleus of an atom to the size of the order of 10 the power 26 meter of extent of the observable universe. Table 2.3 gives the range and order of length and size of some of these objects. We also used certain special length unit for short and large length. These are 1 Fermi is equal to 1 F is equal to 10 the power minus 15 meter. 1 angstrom is equal to 1 angstrom is equal to 10 the power minus 10 meter. 1 astronomical unit is equal to AU, average distance of the sun from the earth, is equal to 1.496 into 10 the power 11 meter. 1 light year is equal to 9.46 into 10 the power 50 meter. Distance that light travel with a velocity of 3 into 10 the power 8 meter per second in 1 year. One parsec is equal to 3.08 into 10 the power 16 minute 16 meter. Parsec is the distance at which average radius of the earth orbits subtends an angle of 1 arc second. Measurement of mass. Mass is a basic property of matter. It does not depend on the temperature, pressure, or location of the object in space. The SI unit of mass is a kilogram kg. The property of the internal standard kilogram supplied by the International Bureau of Weight and Measure BIPM are available in many other laboratories of different countries. In India, this is available at the National Physical Laboratory NPL, New Delhi. New Delhi will will dealing with the atom and molecule. The kilogram is an inconvenient unit. In these cases, there is an important standard unit of mass called the Unified Atomic Mass Units U, which has been established for expressing the masses of atoms as 1 unified atomic mass unit is equal to 1 U is equal to 1 by 12 of the mass of n atoms of carbon, 12 isotopes, C12 isotopes, including mass of electrons is equal to 1.66 into 10 the power minus 27 kg. Mass of commonly available object can be determined by a common balance like the one used in a grocery shop. Large masses in the universe like planet, star, etc., based on Newton's law of gravitation can be measured by using a gravitational method. See chapter 8 for the measurement of small masses of atomic upon subatomic particle, etc. We make use of mass step a spectrograph in which radius of the trajectory is proportional to the mass of a charged particles moving in uniform electric and magnetic field. Range of masses. The masses of the objects we come across in the universe vary over a very wide range. This may vary from teeny masses of order of 10 to the power minus 13 kg of an electron to the Higgs mass of about 10 to the power 55 kg of the known universe. Table 2.4 gives the range and order of the typical masses of various objects. Range and order of length, size of object or distance, length meter, size of a photon 10 to the power minus 15, size of atomic nucleus 10 to the power minus 14, size of hydrogen atom 10 to the power minus 10, length of typical virus 10 to the power minus 8, wavelength of light 10 to the power minus 4, 10 to the power minus 7, sorry. Size of red blood corpus 10 to the power minus 5, thickness of a paper 10 to the power minus 4, height of the Mount Everest above sea level 10 to the power 4, radius of earth 10 to the power 7, distance of moon from the earth 10 to the power 8, distance of sun from the earth 10 to the power 11, distance of Pluto from the sun 10 to the power 13, size of our galaxy 10 to the power 21, distance of Andromeda galaxy 10 to the power 22, distance to the boundary of observable universe 10 to the power 26. Range and order of masses. Object mass kg. Electron 10 to the power minus 13. Proton 10 to the power minus 27. Uranium atom 10 to the power minus 25. Red blood cells 10 to the power minus 13. Dust particle 10 to the power minus 9. Raindrop 10 to the power minus 6. Mosquito 10 to the power minus 5. Grapes 10 to the power minus 3. Human 10 to the power 2. Automobile 10 to the power 3. Boeing 747 aircraft 10 to the power 8, Moon 10 to the power 23, Earth 10 to the power 25, Sun 10 to the power 30, Milky Way galaxy 10 to the power 41, observable universe 10 to the power 55. Measurement of time. To measure any time interval, we need a clock. We now use an atomic standard of time, which is based on the periodic vibrations produced in a cesium atom. This is the basis of the cesium clock, sometimes called atomic clock, used in the national standards. Such standards are available in many laboratories. In the cesium atomic clock, the second is taken as the time needed for 9192631 vibration of the radiations corresponding to the transition between the two hyperfine level of the ground state of cesium 133 atom. The vibrations of the cesium atom regulate the rate of this cesium atomic clock, just as the vibration of a valence wheel regulate an ordinary wristwatch, or the vibrations of a small quartz crystal regulate a quartz wristwatch. The cesium atomic clock are very accurate. In principle, they provide the portal standard, the national standard of time interval second, as well as the frequency is maintained through the four cesium atomic clock. A cesium atomic clock is used at the National Physical Laboratory (NPL) New Delhi to maintain the Indian standard of time. In our country, the NPL has the responsibility of maintenance and improvement of physical standard, including that of the time, frequency, etc. Note that the Indian Standard Time (IST) is linked to this set of atomic clock. The efficient cesium atomic clock are so accurate that they import the uncertainty in time realization as plus minus 1 into 10 the power minus 13 13 example 1 part in 10 the power 13. This implies that the uncertainty gained over time by such a device in less than 1 part in 10 the power 13. They lost or gained no more than 3 micron second in 1 year. In view of the tremendous accuracy in time measurement, the SI unit of length has been expressed in term the path length time travel in certain interval of time 1 by 209 792 458 of a second. Table 2.1. The time interval of events that we come across in the universe vary over a very wide range. Table 2.5 give the range and order of the some typical times intervals. You may notice that there is an interesting coincidence between the number appearing in table 2.3 and 2.5. Note the ratio of the longest and the shortest length of object in our universe is about 10 to the power 41. Interestingly enough, the ratio of the longest and the shortest time interval associated with the event object in our universe is also about the 10 to the power 41. This number 10 to the power 41 comes upon again in table 2.4, which lists typical masses of object. The ratio of largest and smaller masses of the object in our universe is about 10 to the power 41 1 square. Is this is a curious coincidence between these large numbers purely accidental. Accuracy, precision of instrument, and errors in measurement. Measurement is the foundation of all experimental science and technology. The result of our measurement by measuring instrument contain some uncertainty. This uncertainty is called error. Every calculated quantity which is based on measured value also has an error. We shall distinguish between two term accuracy and precision. The accuracy of a measurement is a measure of how close to the measured value is to true value of the quantity. Precision tell us to what resolution or limit the quantity is measured. The accuracy is a measurement may depend on several factors, including the limit or the resolution of measuring instrument. For example, suppose the true value of a certain length is near 3.678 centimeter in one experiment using a measuring instrument of resolution 0.1 centimeter. The measured value is found to be 3.5 centimeter. Will in another experiment using a measuring device of greater resolutions, say 0.01 centimeter, the length is determined to be 3.38 centimeter. The first measurement has more accuracy because it is closer to the true value but less precision. Its resolution is only 0.1 centimeter, while the second measurement is less accurate but more precise. Thus, every measurement is approximate due to error in measurement in general. The error in measurement can be broadly classified as symmetrical errors and random errors. Range and order of time intervals. Event time intervals. Second, lifespan of the most unstable particle 10 the power minus 24. Time required for light to cross a nuclear distance 10 the power minus 22. Period of X-rays 10 the power minus 19. Period of atomic vibration 10 the power minus 15. Period of light wave 10 the power minus 15. Lifetime of an excited state of an atom 10 the power minus 8. Period of a radio wave 10 the power minus 6. Period of a sound wave 10 the power minus 3. Wink of eye 10 the power minus 1. Time between successive human heartbeat 10 the power 0 है. Travel time for light from moon to earth 10 the power 0. Travel time for light from the sun to earth 10 the power 2. Time period of a satellite 10 the power 4. Rotation period of the earth 10 the power 5. Rotation and revolution period of the moon 10 the power 6. Revolution period of the earth 10 the power 7. Travel time for light from nearest star 10 the power 8. Average human lifespan 10 the power 9. Age of Egyptian pyramid 10 the power 11. Time since dinosaurs become extinct 10 the power 50. Age of the universe 10 the power 17. Systematic errors. The systematic errors are those errors that tend to be one direction, either positive or negative. Some of the source of systematic errors: A. Instrumental errors that arise from the error due to impact design or calibration of the measuring instrument. Zero error in the instrument, etc. For example, the temperature graduation of a thermometer may be inadequately calibrated. It may read 104 degrees Celsius at the boiling point of water at STP, whereas it should read 100 degrees Celsius in a Wiener calipers. The zero mark of Wiener scale may not coincide with the zero mark of the main scale or simplify, and ordinary meter scale may be worn off at one end. B. Imperfection in experimental technique or procedure to determine the temperature of a human body. A thermometer placed under the armpit will always give a temperature lower than the actual value of the body temperature. Other external coordination such as charge in temperature, humidity, wind velocity, etc. during the experiment were systematically affected the measurement. Personal error that arise due to an individual B's lack of proper seating of the apparatus or individuals carelessness in taking observation without observing proper precaution, etc. For example, if you by habit always hold your head and beat to for the right wheel reading the position of a needle on the scale, you will introduce an error due to parallax.
Systematic error can be missed by improving experimental technique, selecting better instruments, and removing personal bias as far as possible for a given setup. These errors may be estimated to a certain extent, and the necessary correction may be applied to the reading. Random errors. The random errors are those errors which occurs irregularly and hence are random with respect to sign and size. These can arise due to the random and unpredictable fluctuation fluctuation in experimental condition, unpredictable fluctuations in temperature, voltage supply, mechanical vibrations of experimental setups, etc. Personal unbiased error by the observer taking a reading, etc. For example, when the sample persons repeat the same observation, it is very likely that he may get different reading every time. Least counter error. The smallest value that can be measured by the measuring instrument is called its least count. All the reading or the measured value are good only up to this value. The least count error is the error associated with the resolution of instrument. For example, a vernier calipers has the least count as 0.01 centimeter. A speedometer may have a least count of 0.001 centimeter. Least count error belong to the category of random error, but within a limited size. It occurs with both systematics and random errors. If we used a meter scale for measurement of length, it may have graduations at 1 millimeter division scales, spacing or intervals. Using instruments of higher precisions, improving experimental technique, etc. We can reduce the least count error, repeating the observation several times and taking the arithmetic mean of all observations. The mean value would be very close to the true value of the measured quantity. Absolute error, relative errors, and percentage errors. A. Suppose the value obtained in several measurements are A1, A2, A3, A A n. The arithmetic mean of this value is taken as the best possible value of the quantity under the given condition of the measurement, as a mean is equal to a1 plus a2 plus a3 plus an bracket close upon n, or a mean is equal to n summation I is equal to 1 into ai upon n. This is because, as explained earlier, it is reasonable to suppose that the individual measurements are as likely to overestimate nee, over overestimate overestimate estimate as to underestimate the true value of the quantity. The magnitude of the difference between the individual measurement and the true value of the quantity is called the absolute error of the measurement. This is denoted by del A. In absence of any other method of knowing true value, we consider the arithmetic mean as the true value. Then the error in the individual measurement value for the true value are del A1 is equal to del A1 minus A mean. Del A2 is equal to A2 minus A means. Dot 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 dot. Del n is equal to del a n is equal to a n minus a mean. The del a calculated above may be positive in certain cases of the negative in some other cases, but absolute error del a will always be positive. B. The arithmetic mean of all the absolute error is taken as the final or mean absolute error of the value of the physical quantity A. It is represented by del A mean. Thus, del A mean is equal to in bracket del A1 plus del A2 into plus del a3 plus dot plus del an upon n sum is equal to n summation I is equal to 1 del ai is equal del ai upon n. If we do a single measurement, the value we get may be in the range a mean plus minus del a mean. A is equal to a mean plus minus del a mean, or a mean minus del a mean, del a mean greater than minus greater than a, and greater than mean a mean plus del a mean. This implied that measurement of the physical quantity A is likely to lie between A mean plus del A mean and A mean minus del A mean. C. Instead of the absolute error, we often use the relative error or the percentage error. Del A, the relative error is the ratio of the mean absolute error del A mean to the mean value A mean of the quantity measured. Relative error is equal to del A mean upon A mean. When the relative error is expressed in percent, it is called the percentage error del A. Thus percentage error del A is equal to del A mean upon del A mean into 100%. Let us now consider an example. Example 2.6. Two clocks are being tested against a standard clock located in a national laboratory at 12:00 noon by the standard clock. The reading of the two clocks are clock first, clock second. day है इधर Monday 12 hour 0 minute 5 second, and clock to 10 hour 15 minutes 6 second. Tuesday 12 hour 1 minute 15 second, 10 hour 14 minute 59 second. Wednesday 11 hour 59 minute 8 second, 10 hour 15 minute 18 second. Thursday 12 hour 1 minute 50 second, 10 hour 15 minute 7 second. Friday 10 hour Friday 11 hour 59 minute 15 second, 10 hour 14 minute 53 second. Saturday 12 hour 1 minute 30 second, 10 hour 15 minute 24 second. Sunday 12 hour 1 minute 9 second, 10 hour 15 minute 11 second. If you are doing an experiment that requires precision times interval measurement, which of the two clock will you prefer? Answer. The range of varies over the 7 days of the observation is 162 seconds for the clock first and 31 seconds for clock second. The average reading of clock first is much closer to the standard time than the average reading of clock second. The important point is that a clock's zero error is not as significant for the precision work as it variations, because a zero error can always be easily corrected. Hence, clock second is to be preferred to clock 1. Example 2.7. We measure the period of oscillation of a simple pendulum in successive measurements. The readings turn out to be 2.69 2.63 seconds, 2.56 seconds, 2.42 seconds, 2.71 seconds, and 2.80 seconds. Calculate the absolute error, relative error, or percentage error. Answer: the main period of oscillation of the pendulum t is equal to 2.63 plus 2.56 plus 2.42 plus 2.71 plus 2.80 seconds upon 5 is equal to 13.12 upon 5 seconds is equal to 2.64 second is equal to 2.62 second, as the period are the measured to a resolutions of 0.01 second. All time are to the second decimal. It is proper to put this means period also to the second decimal. The error in the measurements are 2.63 seconds minus 2.62 seconds is equal to 0.01 second. 2.56 second minus 2.62 second is equal to minus 0.06 second. 2.42 second minus 2.62 second is equal to minus 0.20 second. 2.71 second minus 2.62 second is equal to 0.09 second. 2 minus 18 second is minus 2.62 second is equal to 0.18 seconds. Note that the error have the same unit as the quantity to be measured. The arithmetic mean of all the absolute error. For arithmetic mean, we take only the magnitudes in del t means 0.1 plus 0.06 plus 0.20 plus 0.09 plus 0.18 second upon 5 is equal to 0.54 seconds upon 5 is equal to 0.11 second. That means the period of oscillation of the simple pendulum is 0.62 plus minus 0.11 second, i.e. it lies between 2.62 plus 0.11 second and 2.62 minus 0.11 second, or between 2.73 second and 2.51 second, as the arithmetic mean of all the absolute error is 0.11 second. There is already as error in the tenth of a second. Hence, there is no point in giving the period to a hundredth. A more correct way will be to write t is equal to 2.6 plus minus 0.1 second. Note that the last numeral 6 is unreadable, since it may be anything between 5 and 7. We indicate this by saying that the measurement has two significant figure.
In these cases, the two significant figures are two which is reasonable, reliable, and six which has an error associated with it. You will learn more about the significant figure in section 2.7. For this example, the relative error or the percentage error del A is equal to 0.1 upon 2.6 into 10 into 100 is equal to 4%. Combination of error. If we do an experiment involving several measurements, we must know how to the error in all the measurements combined for mass density is obtained by dividing mass by the volume of the substance. If we have errors in the measurement of the mass and of the size or dimensions, we must know what the error will be in density of the substance. To make such estimate, we should learn how error combine in various mathematical operations. For this, we used the following procedures. Error of a sum differences. Suppose two physical quantity A and B have measured value A plus minus del A, B plus minus del B respectively, where del A and del B are their absolute error. We wish to find the error del Z in the sum. Z is equal to A plus B. We have by additions Z plus minus del Z is equal to A plus minus del Z del A plus minus del B. The maximum possible error in Z del Z is equal to A del A plus del B. Z del is equal to del A plus del B. For the difference Z is equal to A minus B, we have Z del plus minus del Z is equal to A plus minus del A minus B plus minus del B is equal to A minus B plus minus del A plus minus del B, or plus minus del Z is equal to plus minus del A plus minus del B. The maximum value of the error del Z is again del A plus del B. Hence, the rule when two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities. Why? How will you measure the length of a line? What a new questions at the stage, you might say, but what if it is not a straight line? Draw a zigzag line in your copy or on the blackboard. Well, not too difficult. Again, you might take a thread place in along the line, open up the thread and measure its length. Now imagine that you want to measure the length of a national highway, a river, the railway track between two stations, or the boundaries between two states or two nations. If you take a string of length 1 meter or 100 meter, keep it along the line, shift it's possible every time. The arithmetic of man hours of labors and expenses on the project is not commensurate with the outcome. Moreover, errors are bound to occur in this enormous task. There is an interesting fact about this. France and Belgium share a common international boundaries whose length mentioned in the official document of the two
countries differs substantially. Go one steps beyond and imagine the coastline where land meets sea. Roads and rivers have fairly mild bend as compared to a coastline. Even so, all documents, including our school books, contain information on the length of the coastline of Gujarat or Andhra Pradesh, or the common boundaries between two states, etc. Railway tickets come within the distance between stations printed on them. We have million stones all along the road indicating the distance to various towns. So how is it done? One has to decide much either one can tolerate and optimize cost effectiveness. If you want a smaller error smaller error, it will involve highly technology and high cost. Sufficient it to say that it required fairly advanced level of physics, mathematics, engineering and technology. It belong to the areas of fractals, which has lately become popular in theoretical physics. Even then, one does not know how much to rely on the figure that props up, as is clear from the story of the France and Belgium. Incidentally, this story of the France Belgium dispersed company descriptional description description appear on the first page of an advanced physics book on the subject of fractals, and shows. Example 2.8. The temperature of two bodies measured by the thermometer are small t1 is equal to 20 degrees Celsius plus minus 0.5 degrees Celsius, and t2 is equal to 15 degrees Celsius plus minus 0.5 degrees Celsius. Calculate the temperature difference and the error therein. Answer T arc is equal to T2 minus T1, 50 degrees Celsius plus minus 0.5 degrees Celsius, minus minus 20 degrees Celsius plus minus 0.5 degrees Celsius. T arc is equal to 30 degrees Celsius plus minus 1 Celsius. Error of B. Error of a product or content. Suppose that Z is equal to AB, and the measured value of A and B are A plus minus AB and B plus minus del B. Then Z plus minus del Z is equal to A plus minus del A, next bracket, B plus minus del B is equal to A B plus minus B del A plus minus A del B plus minus del A del B. Dividing LHS by Z and RHS by AB, where A plus minus del Z upon Z is equal to 1 plus minus del A upon A plus minus del B upon B plus minus del A upon A del B upon B. Since del A and del B are small, we shall ignore their product. Hence the maximum relative error del Z upon Z is equal to del A upon del A plus del B upon B. You can easily verify that this is true for division also. Hence the rule: when two quantities are multiplied or divided, the relative error in the result is the sum of the relative errors in the multipliers. Example 2.9. The resistance R is equal to V upon I, where V is equal to 100 plus minus 5 voltage, and I is equal to 10 plus minus 0.2 ampere. Find the percentage error in R resistance. Answer: the percentage error in V is percentage error in V is 5%, and in I I it is 2%. Total error in R resistance would therefore be 5% plus 2% is equal to 7%. Example 2.10, two resistors of resistance R1 is equal to 100 plus minus 3 ohms, and R2 is equal to 200 plus minus 4 ohms are connected, A in series, B in parallel. Find the equivalent resistance of the A series combination, B parallel combination. Used for A, the relation R is equal to R1 plus R2, and for B, R1 by R is equal to 1 by R1 plus 1 by R2, and del R arc upon del upon R square is equal to del R1 upon del R2 square plus del R2 upon R2 square. Answer: the A. The equivalent resistance of series combination R is equal to R1 plus R2 is equal to 100 plus minus 3 ohms plus 200 plus minus 4 ohms is equal to 300 plus minus 7 ohms. B. The equivalent resistance of parallel combination R arc is equal to R1 R2 upon R1 plus R2 is equal to 200 upon 3 is equal to 66.7 ohm. Then from 1 by R arc is equal to 1 by R1 plus 1 by R2. We get del R arc upon R arc square is equal to del R1 upon del R2 upon del R1 square plus del R2 upon del R2 upon R2 square. Del R arc is equal to R2 square del R1 del R1 upon R1 square plus R arc square del R2 upon R2 square is equal to 16.7 upon 100 square into 3 plus 66.7 upon 200 square into 4 is equal to 1.8. Then R arc is equal to 66.7 plus minus 1.8 ohm. Hence, del R is expressed as 1.8 instead of 2 to keep in conformity with the rules of significant figures. Error in cases of measured quantity raised to a proper. Suppose Z is equal to suppose Z is equal to A square. A square, then del Z upon Z is equal to del A upon A plus del A upon A is equal to 2 del A upon A. Hence, the relative error in A2 is A square in A square is 2 times the error in A. In general, if Z is equal to AP BQ upon C arc, then del Z upon Z is equal to P del A upon A plus Q del B upon B plus R del Q del C upon C. Hence, the rule and the relative error in a physical quantity raised to the power k is the k times the relative error in the individual quantity. Example 2.11, find the relative error in Z if Z is equal to A4B1 by 3 upon CD 3 by 2. Answer in the relative errors in Z is del Z upon Z is equal to 4 del A upon A plus 1 by 3 del B by 3 plus del C by C plus 3 by 2 del D by D. Example 2.12. The period of oscillation of a simple pendulum is t is equal to 2 pi 2 pi bracket 2 pi t is equal to 2 pi under root L upon small g. Measure value of L is 20.0 centimeter, known to 1 millimeter accuracy, and time for 100 oscillations of the pendulum is found to be 90 years using a wrist watch of 1 second resolutions. What is the accuracy in the determination of small g? Answer: small g is equal to 4 pi square L upon t square. Hence t is equal to small t upon small n, and del capital T is equal to del t del small t upon n. Therefore del capital del t capital upon t is equal to del small t upon t small t. The error in both capital L and small t are the least count error. Therefore, del small g upon g is equal to del L upon L plus 2 del capital T upon T is equal to 0.1 upon 20.0. The 2 1 by 19 is equal to 0.027. Thus, the percentage error in G is 100 del G upon G is equal to 100 capital L upon L plus 2 into 100 del capital T upon T is equal to 3%. Significant figures. As discussed above, every measurement involves error. Thus, the result of a measurement should be reported in a way that indicate the precision of the measurement. Normally, the report result of a measurement is a number that include all digits in the number that are known reliably plus the first digit that is uncertain, the reliable digit plus the first uncertain digit are known as significant digits or significant figure. If we say the period of oscillation of a simple pendulum is 1.62 seconds, the digits 1 and 6 are reliable and certain, while the digit 2 is uncertain. Thus, the measured value has three significant figure: the length of an object report after measurement to be to 287.5 centimeter has four significant figures. The digits 2, 8, 7 and 7 are certain, while the digit 5 is uncertain, clearly reporting the result of measurement that include for digit then the significant digits is superfluous and also misleading, since it would give a wrong ideas about the precisions of measurement. The rule for determining the number of significant figure can be understood from the following example. Significant figure indicate, as already mentioned, the precisions of measurement which depend on the least count of the measuring instrument. A choice of change of different unit does not change the number of significant digits or figure in a measurement. This important remark makes most of the following observation clear. First, for example, the length 2.308 centimeter has a four significant figure, but in different units, the same value can be written as a 0.02308 meter or 23.08 millimeter or 23080 micron. All these numbers have the same number of significant figure digits 2, 3 or 0, 8, namely 4. This so that the location of decimal point is of no consequence in determining the number of significant figure. The example gives the following rules. All the non-zero digits are significant. All the zeros between two non-zero digits are significant no matter where the decimal point is it at all. If the number is less than 1, the zero on the right of decimal point but to the left of the first non-zero digit are not significant. In 0.002308, the underlined zeros are not significant. The terminal or trailing zero in a number without a decimal point are not significant. Thus, 123 meter 123 meter is equal to mm, 12,300 centimeter, 12,300 centimeter, and 12,000 1,23,000 millimeter has three significant figure, the trailing zeros being not significant. However, you can also see the next observation. The trailing zeros in a number with a decimal point are significant. The number 3.500 or 0.06900 have four significant figure each. Second, there can be some confusion regarding the trailing zeros. Suppose a length is reported to be 4.700 meter. It is evident that the zeros here are meant to convey the precision of measurement and are therefore significant. If these were not, it would be superfluous to write them explicitly. The reported measurement would have been simply 4.7 meter. Now suppose we change units them. 4.700 meter is equal to 470.0 centimeter is equal to 4,700 millimeter is equal to 0.00470 kilometer. Since the last number has a trailing zero in a number with no decimal, we would conclude erroneously from observation. First, above that the number has two significant figure, while in fact it has four significant figure, and a mere changes of unit cannot changes the number of significant figure. 3. To remove such ambiguities in determining the number of significant figure, the best way is the report every measurement in measurement scientific notation in the power of 10. In this notation, every number is expressed as a into 10 the power b, where a is a number between 1 and 10, and b is any positive or negative exponent or power of 10. In order to get an approximate idea of the number We may round off the number a to 1 or far a greater than 5 and to 10 for 5 less than a 2 less than 10. Then the number can be expressed approximately as 10 the power b, in which the exponent or power b of 10 is called the order of magnitude of the physical quantities. When only an estimate it require the quantity is of the order of 10 the power b. For example, the diameter of the earth 1.28 into 10 the power 7 meter is of other order of 10 the power 7 meter with the order of magnitude 7. The diameter of hydrogen atom 1.06 into 10 the power minus 10 meter is the order of 10 the power minus 10 meter with the order of magnitude minus 10. Thus the diameter of the earth is 17 orders of the magnitude larger than the hydrogen atom. It is an often customary to write the decimal after the first digit. Now the confusion mentioned in a above disappeared. 4.700 meter is equal to 4.700 into 10 the power 2 centimeter is equal to 4.700 into 10 the power 10 the power 3 millimeter, or 4.700 into 4.700 into 10 the power minus 3 kilometer. The power of 10 is irrelevant to the determination of significant figure. However, all zeros appear in the basic number in the scientific notation are significant. Each number in this cases has four significant figure. Thus in the scientific notation, no confusion arise about the trailing zeros in the base number they are always significant. The scientific notation is ideal for reporting measurement, but if this is not adopted, we used the rule adopted in the preceding example. For a number greater than 1 without any decimal, the trailing zero are not significant. For a number with a decimal, the trailing zeros are significant. 5. The digit 0 conventionally put on the left of a decimal for a number less than 1, like 0.1250 is never significant. However, the zeros at the end of such number are significant in a measurement. 6. The multiplying or dividing factor, which are neither rounded numbers nor numbers representing measured value, are exact and have infinite number of significant digits. For example, in r is equal to d upon 2 or s is equal to 2 pi r, the factor 2 is an exact number, and it can be written as 2.0, 2.00 or 2.0000 as required. Similarly, in capital T is equal to small t upon n is an exact number. Rules for arithmetic operation with a significant figure. The result of a calculation involving approximate measured value of quantities value the limited number of significant figure must reflect the uncertainties in the original measured value. It cannot be more accurate than the original measured value themselves, on which the result is based. In general, the final result should not have more significant figure than the original data from which it was obtained. Thus, if mass of an object is measured to be says 4.237 gram for significant figure, and its volume is measured to be 2.51 centimeter cube. Then its density by meter arithmetic division is 1.6880478078 gram per centimeter cube. Up to 11 decimal places, it would be clearly absurd and irrelevant to recorded the calculated volume of density to such a precision when the measurement on which the value is based have much less precision. The following rule of our arithmetic operation with significant figure ensure that the final result of a calculation is shown with the precision that is consistent with the precision of the input measured value. One, the multiplication or division, the final result should retain as many significant figures as are there in the original number with the least significant figure. Thus, in the example above, density should be reported to three significant figure. Density is equal to 4.237 g upon 2.51 centimeter cube is equal to 1.69 g centimeter minus 3 cube. Similarly, if the speed of light is given as 3 into 10 to the power 8 meter per second on a significant figure, and 1 year is equal to 365.25 days, has 3.1557 into 10 to the power 7 seconds, five significant figure. The light year is 9.47 into 10 to the power 15 meter. Three significant figures. Second, in addition or subtraction, the final result should retain as many decimal places as are there in the number with the least decimal places. For example, the sum of the numbers 460 436.32 g, 227.2 g, and 0.301 g by meter arithmetic additions is 663.821 g, but the least precise measurement 227.2 g is the correct to only one decimal place, and the final result should therefore be rounded off to 663.8 g. Similarly, the difference in length can be expressed as 0.307 m minus 0.304 m is equal to 0.003 m is equal to 3 into 10 to the power minus 3 m. Total note that we should not use the rule first applicable for multiplication and division and write 664 g as the result in the example of addition and 3.00 into 10 to the power minus 3 m in the example of subtraction. They do not convey the precisions of the measurement properly. For addition and subtraction, the rule is in term of decimal places. Rounding off the uncertain digits, the result of computation with approximate number which contain more than one uncertain digit should be rounded off. The rule for rounding off number to the appropriate significant figure are obvious in cases a number 2.746 around of to three significant figure is 2.75, while the number 2.743 would be 2.74. The rule by convention is that the preceding digit is raised by leaf the raised by one if the significant digit to be dropped. The underlined digit in these cases is more than 5 and is left unchanged if the latter is less than 5. But what if the number is 2.745, in which the insignificant digit is 5? Here the convention is that if the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1, then the number 2.745 rounded off to 3 significant figure become 2.74. On the other hand, the number 2.735 rounded off to 3 significant figure becomes 2.74. Since the preceding digit is odd in any involved or complex multiply steps calculation, you should retain it in intermediate steps on digit more than the significant digit. The round off to proper significant figure at the end of the calculation. Similarly, a number known to be within many significant figures, such as in 2.99792 into 10 the power 8 meter per second for the speed of light in vacuum, is rounded off to an approximate value 3 into 10 the power 8 meter per second, which is often employed in computation. Finally, remember that exact number that appear in formula like 2 pi in t is equal to 2 pi under root L upon G have a large infinite number of a significant figure. The value of pi is equal to 3.141592 is known to a large number of significant figure. You may take the value as 3.142 or 3.14 for pi with limited number of significant figure with required in specific cases. Example 2.13, each inside of a cube is measured to be 7.203 meter. What are the total surface area and the volume of the cube to appropriate significant figure? Answer: the number of significant figure in the measured length is 4. The calculated area and the volume should therefore be rounded to 4 significant figure. Surface area of a cube is equal to 6 into 7.003 square meter square is equal to 311.299 meter square is equal to 311.3 meter square. Volume of a cube 7.203 meter cube is equal to 373 into 7.14754 meter cube is equal to 333.7 meter cube. Example 2.14, 5.74 gram of a substance occupied 1.2 centimeter cube expressed its density by keeping the significant figure in view. Answer: there are three significant figures in the measured masses, where there are only two significant figures in the measured value. Hence, the density should be expressed to only two significant figure. Density is equal to 5.74 upon 1.2 gram centimeter square minus 3 is equal to 4.8 gram centimeter minus 3. Rules for determining the uncertainty in the result of arithmetic calculation. The rules for determining the uncertainty or error in the number measured quantity in arithmetic operations can be understood from the following example. First, if the length and breadth of a thin rectangular sheet are measured using a meter scale as 16.2 centimeter and 10.1 centimeter respectively, there are three significant figures in each measurement. It means that the length small l may be written as small l is equal to 16.2 plus minus 0.1 centimeter is equal to 16.2 centimeter plus minus 0.6%. Similarly, the width b may be written as b is equal to 10 into 1 plus minus 0.1 centimeter. 10.1 centimeter plus minus 1%. Then the error of the product of two or more experimental value using the combination of error rules will be L B is equal to 163.62 centimeter square plus minus 1.6% is equal to 163.62 plus minus 2.6 centimeter square. This lead us to quote the final result as LB is equal to 164 plus minus 3 centimeter square. Here 3 centimeter square is the uncertainty or error in the essential estimation of area of rectangular sheet. Second, if a set of experimental data is specified to a significant figure, a result obtained by combining the data will also be valid to a small and significant figure. However, if data are subtracted, the number of significant figure can be reduced. For example, 12.9 g minus 7.06 g, both specified to three significant figures cannot properly be evaluated as 5.84 g, but only as 5.8 g, as uncertainties in subtraction or addition combine in a different fashion. Smallest number of decimal places rather than the number of significant figure in any of the number added or subtracted. The relative error of a value of number is specified to significant figure depends not only on n but also on the number itself. For example, the accuracy in a measurement of mass 1.02 gram is plus minus 0.1 gram, whereas another measurement 9.89 gram is also accurate to plus minus 0.01 gram. The relative error in 1.02 1.02 gram is equal to plus minus 0.01 upon 1 minus 0.02 into 100% is equal to plus minus 1%. Similarly, the relative error in 9.89 gram is equal to 1 plus minus 0.01 upon 9.89 into 10 the power into 100 है 100% is equal to plus minus 0.1%. Finally, remember that intermediate result in a multiply steps computation should be calculated to one more significant figure in every measurement than the number of digits digits in the least precise measurement. These should be justified by the data, and then the arithmetic operations may be carried out. Otherwise, rounding errors can build upon. For example, the reciprocal of 9.58 calculated after rounding off the same number of significant figure 3 is 0.104, but the reciprocal of 0.104 calculated to 3 significant figure is 9.62. However, if we had written 1 by 9.58 is equal to 0.1044 and then taken the reciprocal to 3 significant figure, we would have retrieved the original value of 9.58. This example justify the idea to return on more extra digit than the number of digit in the least precise measurement. In intermediate steps of complex multiple steps calculated in order to avoid additional error in the process of rounding of the number.
Dimensions of physical quantities. The nature of physical quantities is described by its dimensions. All the physical quantities represented by derived unit can be expressed in terms of some combination of seven fundamental or base quantities. We shall call these based unities as the seven dimensions of physical world, which are denoted with square square brackets. Thus, length has the dimension L, mass capital M, time capital T, electric current capital A, thermodynamic temperature capital K, luminous intensity small c.d., and the amount of substance mole. The dimensions of physical quantities are the powers or exponents to which the base quantities are raised to represent that quantity. Note that using the square brackets around a quantity means that we are dealing with the dimensions of the quality. In mechanics, all the physical quantities can be written in terms of the dimensions capital square bracket L and square bracket M and square bracket T. For example, the volume occupied by an object is expressed as the product of length, breadth, and height, or three length. Hence, the dimensions of volume are L is equal to L3Q or L3Q. L3Q. LQ3. As the volume is independent of mass and time, it is said to possess zero dimension in mass m m0, zero dimension in time t0, and and three dimension in the length. Similar force as the product of mass and acceleration can be expressed as force is equal to mass into acceleration. Mass into length upon time square. The dimension of force are ml upon t square is equal to mlt minus 2. Thus, the force has one dimension in mass, one dimension in length, and minus two dimensions in time. The dimension in all other base quantities are zero. Note that in these types of representation, the magnitude are not considered. It is the quality of the types of physical quantity that enters. Thus, a change in velocity, initial velocity, average velocity, final velocity, and speed are all equivalent in this context. Since all these qualities can be expressed as length upon time, their dimensions are L upon T or LT minus 1. Dimensional formula and dimensional equations. The expression which show how and which of the base quantities represent the dimensions of a physical quantity is called the dimensional formula of the given physical quantity. For example, the dimensional formula of the volume is M naught M0 L3 T0, and that of speed or velocity is M0 L T minus 1. Similarly, M0 L T minus 2 is the dimensional formula of acceleration, and ML minus 3 T0 that of mass density. An equation obtained by equation a physical quantity with its dimensional formula is called the dimensional equation of the physical quantity. Thus the dimensional equation are the equation which represent the dimensions of a physical quantity in term of the base quantities. For example, the dimensional equation of volume v, speed v, small v, force capital F, and mass density P may be expressed as V is equal to M0L3 T0. Small v is equal to M0LT minus 1. F is equal to MLT minus 2, and T is equal to ML minus 3 T0. The dimensional equation can be obtained from the equation representing the relations between the physical quantities. The dimensional formula of a large number and wide variety of physical quantities derived from the equations representing the relationship among other physical quantities and expressed in terms of base quantities are given in appendix 9 for your guidance and ready reference. Dimensional analysis and its application. The recognition of concept of dimensions which guide the descriptions of physical behavior is of basic importance, as only those physical quantities can be added or subtracted which have the same dimensions. A thorough understanding of dimensional analysis help us in deducing a certain relation among different physical quantities and checking the derivations accuracy and dimensional consistency or homogeneity of various mathematical expressions. When magnitude of two or more physical quantities are multiplied, their units should be treated in the same manner as as ordinary algebraic symbol, which we can cancel identical unit in the numerator and denominator. The same is true for dimensions of a physical quantity. Similarly, physical quantity is represented by symbol on both sides of a mathematical equations must have the same dimensions. Checking the dimensional consistency of equations, the magnitude of physical quantities may be added together or subtracted from one another only if they have the same dimensions. In other words, we can add or subtract similar physical quantities. Thus, velocity cannot be added to force, or an electric current cannot be subtracted from the thermodynamic temperature. This is simple principle called the principles of homogeneity of dimensions in an equation is extremely useful in checking the correctness of an equation. If the dimension of all terms are not same, the equation is wrong. Hence, if we derived an expression for the length or distance of an object regardless of the symbol appearing in the original mathematical relation, when all the individual dimensions are simplified, the remaining dimensions must be that of length. Similarly, if we derived an equation of speed, the dimensions on both the side of equation when simplified must be of length time or LT minus 1. Dimensions are customarily used as a preliminary test of consistency of an equation when there is some doubts about the correctness of the equation. However, the dimensional consistency does not guarantee correct equation. It is certain to extent of dimensionless quantities or functions. The argument of special functions such as the trigonometry, logarithmic, and exponentaneous function must be dimensionless. A pure number ratio of similar physical quantities such as angle as the ratio length upon length, refractive index as the ratio speed of light in vacuum, speed of light in medium, etc., has no dimensions. Now we can test the dimensional consistency or homogeneity of the equation. X is equal to x and not plus v naught t plus 1 by 2 at square for the distance x traveled by a particle or body in time t, which start from the positions x naught with an initial velocity v naught at time t is equal to 0 and has uniform acceleration along the direction of motion. The dimensions of each term may be written as x is equal to L and x naught is equal to L and v naught t is equal to L t minus 1 t is equal to L. Square bracket under 1 by 2 at square is equal to lt minus 2 t2 is equal to L, as each term on the right hand side of this equation has the same dimension, namely that of length, which is same as the dimensions of left hand side of the equation. Hence this equation is a dimensionally correct equation. It may be noted that a test of consistency of dimensions tell us no more and no less than a less than a test of consistency of a unit, but has the advantage that we need not submit ourselves to a particular choice of unit, and we need not worry about conservation among multiple and sub-multiple of the unit. It may be born in a mind that if an equation fail this consistency test, it is proved wrong, but if it passes, it is not proved right. Thus a dimensionally correct equation need not be actually an exact correct equation, but a dimensionally wrong, incorrect, or inconsistent equation must be wrong. Example 2.15. Let us consider an equation half mv square is equal to mgh, where m is mass of the body, v its velocity, and g is the acceleration due to gravity, and h is the height. Check whether this equation is dimensionally correct. Answer: the dimension of LHS are m lt minus 1 lt minus 1 square bracket square is equal to m L2 t minus 2 is equal to m L2 t minus 2. The dimensions of RHS are m Lt minus 2 L is equal to m L2 t minus 2 is equal to m L2 t minus 2. The dimension of LHS and RHS are same, and hence the equation is dimensionally correct. Example 2.16. The SI unit of energy is J is equal to kg meter square per second square. That of speed velocity V is meter per second, and acceleration of A is meter per second square meter per second. Which of the formula of kinetic energy K given below can you rule out on the basis of dimensional arguments? Small m standard for mass of the body. A. K is equal to m square V Q K B. K is equal to half mv square. C. K is equal to ma. D. K is equal to 3 by 60 mv square. E. K is equal to half mv square plus ma. Answer: every correct formula or equation must have the same dimension on both sides of the equation. Also, only quantities with the same physical dimensions can be added or subtracted. The dimensions of quantity on the right side m2 L3 t minus 3 for a m L2 t minus 2 for B and D m L t minus 2 for C. The quantity on the right side of E has no proper dimension, since two quantities of different dimensions have been added. Since the kinetic energy K has the dimensions of ml2 t minus 2, formula A, C and E are ruled out. Note that dimensional arguments cannot tell which out the two B or D is the correct formula for this. One must turn to actual definition of kinetic theory. See chapter 6. The correct formula of kinetic energy is given by B. deducing a relation among the physical quantities. The method of dimension can sometimes be used to deduce the relation among the physical quantities. For this, we should know the depends of the physical quantity on other quantities. Up to three physical quantities are linearly independent variable and consider it as a product type of the dependence. Let us take an example. Example 2.70. Consider a simple pendulum having a bob attached to a string that oscillates under the action of the force of gravity. Suppose that the period of oscillation of the simple pendulum depends on its length, L, mass of the bob, and acceleration due to gravity, G. Derive the expression for its time period using method of dimension. Answer: the dependence of time period t on the quantities small l, g, and m as a product may be written as capital T is equal to small k, l, x, g, y, and m, z, where k is a dimensionless constant and x, y, and z are the exponents. By considering dimensions on both sides, we have L0 M0 T1 is equal to L1 x L1 T minus 2 y m L1 z is equal to L x y L x plus y T minus 2 y m z. On equating the dimensions on both sides, we have x plus y is equal to 0 minus 2 minus 2y is equal to 1 and 0 z is equal to 0, so that x is equal to 1 by 2, y is equal to minus 1 by 2, z is equal to 0. Then t is equal to k l half g minus half, or t is equal to k under root a small l upon small g. Note the value of constant k cannot be obtained by the method of dimension. Here it does not matter if some number multiplies the right side of this formula, because that does not affect its dimensions. Actually, k is equal to 2 pi, so that t is equal to 2 pi under root small l upon small g. Dimensional analysis is very useful in deducing a relation among the interdependent physical quantities. However, dimensionless constant cannot be obtained by this method. The method of dimensions can only test the dimensional validity, but not the exact relationship between physical quantities in any equation. It does not distinguish between the physical quantities having same dimensions. A number of exercises at the end of this chapter will help you develop skill in dimension analysis. Okay, ठीक. Summary: physics is a quantitative science based on measurement of physical quantities. Certain physical quantities have been chosen as fundamental or base quantities, such as length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. Each base quantity is defined in terms of a certain basic arbitrarily chosen but properly standardized reference standard called unit, such as meter, kilogram, second, ampere, Kelvin, mole, and candela. The unit for the fundamental or base quantities are called fundamental or base unit. Other physical quantities derived from the base quantities can be expressed as a
combination of the base unit and are called derived unit. A complete set of units, both fundamental and derived, is used a system of units. The international system of units of SI based on 7 base unit is at present internationally accepted unit system and is widely used throughout the world. Thus, SI units are used in all physical measurement for both the base quantities and the derived quantities obtained from them. Certain derived units are expressed by means of SI unit with special names such as Joule, Newton, and Newton watt, etc. The SI units have a well-defined and internationally accepted unit symbol such as m for meter, kg for kilogram, s for second, a for ampere, n for Newton, etc. Physical measurements are usually expressed for small and large quantities in scientific notation with the power of 10. Scientific notation and the prefix are used to simplify measurement notation and numerical computation, giving indication to the precisions of the numbers. Certain general rules and guidelines must be followed for using a notation for physical quantities and standard symbol for SI unit, some other unit and SI prefix for expressing properly the physical quantities and measurements. In computing any physical quantities, the unit for derived quantities involved in the relationship are treated as though they were algebraic quantities till the desired unit are obtained. Direct and indirect method can be used for the measurement of physical quantities. In measured quantities, while expressing the result, the accuracy and precision of measuring instrument along with the errors in measurement should be taken into account. In measured the computed quantities, proper significant figure only should be retained rules for determining the number of significant figure, carrying out arithmetic operations with them, and a rounding of the uncertain digit must be followed. The dimensions of base quantities and the combination of these dimensions describe the nature of physical quantities. Dimensional analysis can be used to check the dimensional consistency of equation, deducing relations among the physical quantities, etc. A dimensionally consistent equation need not be actually an exact correct equation, but a dimensionally wrong or inconsistent equation must be wrong. तो यार यहाँ पर हमारा यूनिट्स एंड मेजरमेंट सेकंड चैप्टर खत्म हो गया है, ठीक है। और इसके बाद चैप्टर आएगा इधर, तो एक्सरसाइज है, एक्सरसाइज को भी हम कवर करेंगे जल्दी। और इधर देख लो थर्ड चैप्टर स्टार्ट हो जाएगा, मोशन इन स्ट्रेट लाइन, इसको कवर करना है, ठीक है, रीडिंग करना। तो आज का इतना हो गया है, ठीक है, मिलते हैं नेक्स्ट वीडियो में।